question 3, we're asked to derive the reduction of order formula, this boxed equation here. Now, in your lectures, you didn't have time to complete the proof of this formula. So in this video, I'm just going to go through the proof of this formula using the method that's outlined in your lecture notes. In the tutorial sheet, you're asked to use an alternative method to the one outlined in your lecture notes. So what I'll do is I'll upload both sets of solutions. I'll upload the proof of this formula using the method that's outlined in your lecture notes, which I'm going to be covering in this video, and I'll also outline the proof using the alternative method that's described in the tutorial sheets. So what does this theorem say? Well, as I mentioned, it's theorem 1.5 in your typed lecture notes. It says really two things. The first is that, let's just say we're given a homogeneous linear second order differential equation, equation 1 here. Suppose we have two linearly independent solutions to this equation, which we call y1 and y2. Well, the theorem says two things. The first thing it tells us is that the Wronskian W of those two solutions that satisfies this boxed equation here, this first order linear ODE in W. Now this formula is known as Abel's formula. Now using Abel's formula, you can prove a much more useful formula, the so-called reduction of order formula, which is the second part of the theorem. The reduction of order formula says that if we have one of the solutions to the differential equation, let's just say y1, then we can automatically determine the second solution, y2, using this formula here. That's incredibly powerful, because if we know one of the solutions using any method, then we can automatically determine the second linearly independent solution and hence determine the general solution to the equation. So in this video, I'm going to break it down into two parts. In the first part of the video, I'm going to derive Abel's formula, and in the second part, I'm going to show how you can use Abel's formula to derive the reduction of order formula. So let's start with deriving Abel's formula. Well, before we do that, let's just introduce a little more information. So we're given two solutions to equation 1, which I've called y1 and y2. Well, if y1 and y2 are solutions to the equation, then they both have to satisfy the equation. So this is where I got equation 2 and 3 from. y1 and y2 both satisfy equation 1, which gives me equation 2 and equation 3. I've also introduced the Wronskian of those two solutions, which I've called W, and W here is y1, y2 prime minus y2, y1 prime, the Wronskian of y1 and y2, which I've labeled equation 4. So we're going to show how you can use equations 2, 3, and 4 to derive Abel's formula. So to derive Abel's formula, what we're going to do is we're going to differentiate both sides of equation 4 with respect to x. So if we differentiate 4, what do we get? Well, the left-hand side, the derivative of w with respect to x, that's simply w prime. Prime denotes derivative with respect to x. Now, to differentiate the right-hand side, we're going to need to use the product rule twice. So the first derivative, that's just going to give us y1, y2 double prime plus y2 prime, y1 prime, and then the second term is going to give us y2, y1 double prime minus y1 prime, y2 prime. So if we look a little closer at this equation, we can see that we have two second derivative terms, y2 and y1 prime. So let's eliminate all of the second derivative terms in this equation here. So how are we going to do that? Well, to do that, we can use equations 2 and 3. you can see that if you rearrange equation 2 to solve for y1 double prime, then we can see that y1 double prime is going to be equal to minus p y1 prime minus q y1. Similarly, we can solve equation 3 for y2 double prime. And then substituting both of those expressions into our equation here for w prime, we can eliminate all of the second derivative terms. So, doing that, what do we get? Well, we get y1, y2 double prime. Well, that's just going to be minus p y1 prime minus q y1. And then the second term here, well, that just stays as is because it has no second derivative terms. So that just stays as y2 prime, y1 prime. Now the third term here, y2, well, y1 double prime. Sorry, the ones here should have been 2. Well, the y1 double prime, as I mentioned, we can solve equation 2 for y1 double prime. And that gives us minus p y1 prime minus q y1. And then this second term here stays as is. y1 prime, y2 prime, because it has no second derivatives. Now, let's just multiply out all of this. And what do we get? Well, if we multiply out the first term, we're just going to get minus p y1 y2 prime minus q y1 y2 plus p y1 prime y2 and then plus q y1 y2. Next, if we inspect this expression a little closer, we can notice that, well, the second and third term, they will cancel each other out because they're both q, y1, y2. And then we're just left with the first term and the third term. Well, notice these terms here, they have a common factor of p. So let's just factor out, let's just say minus p from both of these expressions. And that will leave us with minus p y1 y2 prime minus y1 prime y2. Well, of course, this is the same thing as saying, well, we can leave the first term alone, y1 y2 prime. We can flip the order on the second term. You'll see why I did that in a second, and write it as y2 y1 prime. Well, if you notice this bracketed term here, that's just simply the Wronskian of y1 and y2 w. So this expression here is simply minus p w. So we've shown here that w prime is equal to minus p w. So w prime is equal to minus p w, which of course is exactly Abel's formula, just in an alternative form, just using the prime notation for the derivative as opposed to the fractional notation. So by differentiating w and just eliminating the second derivative terms for y1 and y2, we were able to derive Abel's formula. In the next video, I'll show how you can use Abel's formula to derive the reduction of order formula.